My name is Mohammed Ismail. I'm a PhD student at the MIT School of Architecture and Planning, and I'm here to present our paper entitled Immersive Design of Exposed Optimized Structural Systems. This paper is done in collaboration between the Digital Structures Research Group at MIT and Mindesk Incorporated, who I'll introduce later on in this presentation. The result of this work, as you can see, is a tool that allows for the immediate visualization and evaluation of a shape-optimized concrete structure through the use of parametric modeling, machine learning, and virtual reality. This work is largely motivated by, I think, something that motivates most of us here. We are currently experiencing unprecedented waves of urban construction. As a result, our global building stock is expected to double in area by 2060. This is the equivalent of adding an entire New York City every month for 40 years to the world. This makes us especially aware of the greenhouse gases that are associated with construction. As we all probably know, about 40% of the global emissions are due to building construction operations. And while operations of buildings, lighting, heating, cooling are becoming more and more efficient, we're still doing very little to deal with the 30% of building associated emissions just due to the embodied cost of materials, manufacturing, transportation, and construction. And so really a lot of this work is motivated by the desire to deal with that untapped 30% of embodied carbon from construction. As we all know, we have excellent tools for architectural drafting and design. We have tools for structural analysis, and we have many methods for the evaluation of a finished architectural product. But we have far fewer tools that connect all three stages of the design and construction process. And so if we want to deal with the demands and ecological costs of construction, we really need better methods for real-time design and performance evaluation. Another possible motivation for this work, and you'll see why shortly, is the expression of structure. For centuries, architectural theorists and designers have advocated for the honest expression of building structure. People like Viollet-le-Duc used to champion the honesty of materials. This was something that was echoed in David Billington's definitions of structural art, which is why we celebrate the works of people like Pierluigi Nervi and Mahendra Raj. Even now, you can find home improvement blogs that post about exposed beams and products like faux wood beams that reflect a desire by the end user to showcase the structural behavior of the building, even if it is artificial. One way we can enable performance-driven structural design is through the use of virtual and augmented reality. Over the last 5 to 10 years, a lot of excitement about AR and VR has emerged in the AEC industries, and this is largely focused on visualizing a crystallized design or interpreting the results of a single analysis model. Some of the more exciting work aims to use AR to guide the construction process, but really little has been done to use VR to explore our actual design options, allowing us to iterate over design space while evaluating the building performance. And this is where our co-authors Mindesk come in. As discussed, we have many tools that allow for the iterative design and analysis through CAD and parametric modeling. But we also now have a number of increasingly accessible and affordable technologies that enable building evaluation through VR before the construction actually occurs. But there's still a large gap that exists between these kinds of tools. And this is a gap that Mindesk aims to fill. Mindesk is a real-time platform that enables a live link between CAD, in this case, we're going to be using Rhino and Grasshopper, and virtual reality. And this enables the visualization and intuitive parametric modeling of the user. For instance, allowing a real-time interaction between the designer and the model, which then gives immediate evaluation and visualization during the design process and not after. The framework of this work looks like this. It takes the initial design inputs from the user. It uses a trained neural network model to predict the ideal geometry of a shaped concrete slab and visualizes it in VR using Mindesk's platform. As you can see, Mindesk also allows the user to manipulate the inputs and iterate through the design options in real time, thanks to the speed of the predictive neural network model. For this paper, we used the case study of a shape-optimized concrete structure as an alternative to the flat slab construction occurring worldwide. We reference a previously published method for the shape optimization of concrete slabs, and this is a method that uses constrained optimization and analytical structural analysis to minimize the embodied energy of a concrete slab. As you can see, the method iterates through hundreds of designs until it finds the minimal design that meets the structural and fabrication constraints or whatever other constraints we put on the design. This optimization can take up to 40 minutes, which really makes it impractical for real-time design and analysis. As a note, this video was substantially sped up for this presentation. And this is why machine learning can actually help predict the ideal geometry in a much shorter time. We trained a neural network model using 256 samples that were collected using the Cobila algorithm from the NLOpt Python library, which is publicly available. The neural network model looks something like this. It was trained to predict the design of a shaped concrete slab according to 4 user inputs. For the purposes of this paper, these inputs were the strength of steel and concrete, the maximum depth of the slab, and the slab's clear span. The model then predicts the ideal geometry, approximating the results of constrained optimization for the same structural conditions. This then results in a tool that in real time predicts a shaped slab according to those user inputs. And so this video, unlike the last one, was not sped up. This is just what it looks like in real time. We can then reanalyze those results of the predictive model to make sure that it meets the structural conditions that it was designed for. And it won't always work, but most of the time it gives you feasible shaped slab designs, which perhaps more importantly can then be used to visualize the real-time evaluation of a full building system, where we might do something like trying to figure out the embodied energy per square meter of floor area or the mass per square meter of the structure. And this enables a fairly rapid iterative design and evaluation process for early stage structural design. And once again, using Mindesk, this can all occur in virtual reality, enabling us to see the ramifications of our design decisions as though we were in the space after construction. We can also revisit the design of singular elements and check them for structural capacity or aesthetic expression. So in conclusion, the environmental costs of construction require far more holistic methods of performance-oriented design than what we have today. The method presented in this paper could enrich structural design by pairing virtual reality and interaction with machine learning predictive modeling for real-time evaluation. And this research was largely made possible by increasingly accessible tools for visualization and evaluation. So I'd really like to end with a broader question for all of us. Can we use these tools to account for the needs of our end users and their desires in our low carbon design processes? With that, I would like to thank you all for listening, and I look forward to our discussion.